Good morning, good afternoon, good evening, everyone. Thanks for joining this webinar. And this webinar is supported by ISMGE TC 306. It's a committee on geoengineering education committee. So the chair of the committee is Professor Marina Pantazudu. So she will introduce the speaker and talk about her committee. So again,
Thank
Marina,
you.
please take it over.
Thank you, Krishna, for giving me this this opportunity. Professor Albert Valocchi is the Abel Bliss Professor Emeritus in the Department of Civil Engineering at the University of Illinois at Urbana-Champaign. And he started there in 1981 after completing his PhD at Stanford University. In his research, he studies problems of groundwater contamination and resource sustainability, carbon dioxide sequestration, and impacts of model uncertainty on managing groundwater resources. He has published about 150 papers in peer-reviewed journals, and for 8 years, he was editor-in-chief of the prestigious Journal of Contaminant Hydrology. Today, he's going to talk about work he has done to help all of us teaching our courses. This is a very special webinar. As Krishna said, it is supported by 3 technical committees on education, on numerical modeling, and on environmental geotechnics. The invitation was initiated by the Committee on Education, but I'm not speaking now representing TC306. I'm speaking as an instructor of a course on environmental geotechnics, using for over 15 years a suite of models for contaminant transport in groundwater developed by Professor Valocchi and co-workers. Fortunately, they also wrote a paper about it, and this is how I discovered them. It is a great paper because it discusses possible implementation alternatives and the rationale for the final decision. I have posted the link of the reference in the chat box. They have 2 papers, you'll find both links there. For an educational software, a useful life for more than 25 years now is a miracle. And we will hear today how this miracle was achieved. There is one last thing I would like to share from my experience with the models. One of them solves numerically a partial differential equation, and I was playing with it and discovered some problematic results. I emailed Professor Valocchi, it's many years ago now, whom I have never met. I met him today. And to my surprise, he replied promptly. He thanked me and said he will look into it. Within a couple of days, he wrote again, the problem was found and fixed. So this story is a partial explanation of the miracle. Professor Valocchi, it's your turn now.
Okay, thank you very much for the introduction. And it's the first time anyone has referred to any of my work as a miracle. So I will remember this. So I'm going to share my screen now, and let's see. Hopefully this will work here. Is everyone hopefully you can see my screen?
Yeah, looks
Yes.
good.
Okay. Okay, so let me just go here. Okay, so again, I'd like to thank you for allowing me to start off your seminar series in year 2025. This is going to be no research here. As Professor Pantazudu mentioned, this is about a suite of interactive models that we developed over many years, starting from back in the other century, actually, to support instruction in groundwater hydrology and contaminant transport. And I know that I know that at least Professor Pantazudu has used these in environmental geotechnic courses, and I'm hoping that with the exposure today, some of you will also find these interactive models useful. And I appreciate it if you would, tell me how you use the models And also feel free to tell me when there's a problem, because sometimes there are problems. So, okay. So we all know that for our teaching, mathematical simulation models are important pedagogical tools. And more than 25 years ago, we were, mainly in our teaching, we use very simple analytical solutions that could be computed or in tables. And we wanted to look at some of the easiest ways that we can incorporate these tools into mainly introductory courses and be able to use these tools in lecture demonstrations and student exercises. So what I'm going to do today is kind of go back in history, back to around the turn of the century, 1999, 2000, talk about the state of the internet and other things back then. I'll talk about how we've dealt with several technical roadblocks along the way so that we can keep these models up and running for now more than 25 years. I'm not going to get into a lot of the computer software details because I don't really understand them all, but I'll try to give you the basic some of the basic issues. I will then, in my presentation, sort of explain all the models that we developed and show some slides about a few of them. And then I'll go out of the PowerPoint and I'll do a few real-time demos. And at that point, I'm happy to take any questions or comments that you might have. So here's kind of where this slide here shows sort of the situation, say about 25 years ago. We had some nice software that was developed by usually by government agencies, sometimes by consulting firms. These models were developed for other purposes, not for education. I'm showing here a suite of models developed by the United States Geological Survey on the left. On the right is a spreadsheet program that was developed for a contractor for the U.S. Environmental Protection Agency. That was for natural attenuation and bioremediation. But these were still required. If you wanted to use these, students would have to download the software, learn how to install the program, and there was quite a learning curve. And the other thing that was going on back around the turn of the century was that the web browsers were really coming into prominence. And students, we noticed in classes, really liked web browsers. They were clicking and searching and doing all kinds of fun things. So we thought, is there any way that we can make these so easy that students could even use them through a web browser? And then, we looked at some models for implementing this. And there are two basic ways that we could use the web to do this. What's shown on the left is a server client model where all the programs are actually running on a central server, and then the student sitting with their laptop would be the client, and they would send commands over the internet to run a program. The program would execute, the results would be generated and then sent back to the student. So this has a lot of flexibility. You can run very complicated models on a more powerful computer, but back especially then, there was always reliability with the network, and it was slow, and there would be bottlenecks. So the other option is shown here on the right, and that's where everything is executed locally by the client. So there would still be web pages hosted on a server like all web pages are, but everything would be done locally. And this we decided to implement these in Java, because at that point Java could be executed within a web browser. So a Java applet is the way that we implemented these codes. And these are, computer programs that were written in the Java programming language. It was self-contained, like I mentioned. There was no additional software needed. Flexible, easy to use. Since everything's being done locally on the web browser, with at the student's laptop, everything works almost instantly. You can modify input data, assess the impact of parameter changes. You can get some flexible graphical display of output of the model results. We also implemented options that you could download or display the numerical output, the raw numerical output, and then you could copy that and paste it into other software. So students often would do that and paste into Excel and do additional plotting or other analysis in Excel. The applets had tutorials that included both something on model theory and user interface. And these also were easy to use during a lecture and class demonstration. So everything was working great for a while, and then some problems came about because of Java security problems. So when a Java applet is, and like I said, I'm not a computer scientist, but in order to run these Java applets on a web browser, the web browser needed a plugin, which was called the Java Virtual Machine. And this is the plugin that allowed the codes to run within the web browser. And up to about, for the first 10 years, almost all web browsers automatically came packaged with this Java Virtual Machine. So we didn't have to worry about anything. But then these Java applets had the potential to access system resources outside the browser on the client's computer. And this resulted in these applets being very vulnerable to security exploits, and people were having a lot of problems with their computers being taken over by bad agents. And so web browsers then stopped supporting Java applets. So we had to figure out how we could continue to keep these models useful to the community. I mean, one option was to totally rewrite everything in some new software, but that was too much work. So how can we continue today to use these Java applets? And so basically there are two options. One is there's an extension that is a free extension for Chrome and Edge. It's called ChirpJ. So, and this basically this extension will convert this Java code to something called JavaScript, which only runs within the browser and cannot go outside the browser, and so it's secure. And so this is one option, is to install this browser extension. And again, this is available for Chrome and Edge. Sometimes there's some glitches when this does the conversion. The other way that the applets can be executed is that you can go to the website, which I'll show in the next slide, and you can, as long as you have Java installed on your computer, on your laptop, which is free and easy to install. It's called the Java Runtime Environment. You can go to the website and you can download the entire applet to your own computer, your client, to your laptop, and then you can click and run and do everything locally. So, that's the second option. So here is the way this is the website, the way it looks. There's the web address up at the top. And let's see if you can, hopefully you can see my cursor there. I'm just going to go through and list each one of these models that we've developed. And again, the motivation initially was to support our classes in groundwater hydrology, contaminant transport, contaminant fate and transport in the environment. So and down below, should mention, I would definitely acknowledge all the people that worked on this as a team. I'll also mention this at the end. Is my colleague, Professor Charlie Worth, who was at Illinois, now at University of Texas. He was teaching classes in contaminant fate and sorption and desorption. And so we developed some models to simulate diffusion into and out of spherical particles with adsorption and reaction. And then we have a whole series of models for one-dimensional contaminant transport. So the first and simplest one of the first ones we developed is to just have equilibrium sorption with first order decay. And then we wanted to study the possibility of mass transfer limited adsorption and desorption. So we implemented another model, which is more complicated. We also were interested in problems related to radioactive decay and sequential biological transformation of contaminants. So we implemented this model here, where we have multiple contaminants, multiple solutes with sequential decay. Coming here to the middle, excuse me, yes?
We cannot see your cursor.
Oh, let me, okay. Let me, no, hold a second here. Let me see if I can, Sorry, let me see if I can, oh, hold a second here, sorry. Yeah.
The laser pointer would be good.
Laser pointer, okay, let me try laser pointer here. Oh, there we go, okay.
Yep,
Now you can see.
that's good.
Okay.
Yeah.
Thank you. Okay, so here is a set where we wanted to go beyond one-dimensional dispersion problems. So we implemented, again, uniform flow with two-dimensional and three-dimensional dispersion. And these we use for applications related to leaking from landfills and continuous sources. Down below is one that in the groundwater hydrology class, we do standard parameter estimation from pumping tests using the Tice curve fitting method. And for many, many years, I taught the good old fashioned way, where we would plot the results from a drawdown test on graph paper, and we would have these type curves, and we would do this graphical curve fitting by hand. And the new generation of students don't like to graph things by hand on graph paper anymore. And so we implemented a very kind of a cool way to do this with an applet. Down here is one that I'll mention at the end. This is a different application which uses the other model where we run ModFlow on a server, and so we are doing the modeling a slightly different way. And so I'll mention this also at the end. But this is for studying interaction between groundwater and stream flow. And then here is some applications for two-dimensional steady flow in aquifers, either homogeneous aquifers or heterogeneous aquifers, where we track streamlines and particle path. And this would be we've used these to study things like groundwater capture and dispersion, studying macro dispersion and dispersion caused by heterogeneous flow paths. So let me go to just show a couple of screenshots from some of the more commonly used models. This first one here is one of the first ones that we developed, one-dimensional transport. So this is a screenshot from the tutorial page. So we have, say, a soil column with constant flow, and our input, we might have an initial concentration in the column, and then at some time 0, we change to another continuous value, usually a higher value of contaminant, and then after a certain period of time, we drop back to the initial value. And so here is the governing equation, pretty simple. And these are the processes that we have implemented: advection, dispersion, linear equilibrium sorption, and we have first order decay. And this is and we could have either a first type boundary condition or third type boundary condition. We also have the possibility that the input conditioning can also have first order decay in time. And then this is just one example of one of the analytical solutions to give you an idea of what it looks like mathematically. And complementary error functions and exponentials, and this can be pretty easily programmed in Java. And then again, this is a screenshot of the case for the third type boundary condition. And what I've shown here is this would be, if you look here, this shows the type of output that we select. So this is a spatial profile at a fixed time. And what we've done here is we've plugged in 2 different dispersion coefficients. And here there's these windows here where you can change any of the input parameters: retardation factor, velocity, dispersion coefficient. And what we're doing here is showing the effect of a change in dispersion. I think the original dispersion coefficient was 0.5, and we changed it to 0.1, so students can see that the contaminant front is more steep than it was before. The other thing that we can do is, I'll show this in the demonstration, there's a cursor that you can move back and forth. And when you move the cursor, you get an automatic printout of the distance where you are. In this case, it's here, and it prints out what the values of the concentration are for the 2 different cases. So that's this option here for multiple curves. You can click a button here that does show data, and then these windows over here on the right pop up, which shows all the raw data that's used for each one of these computations. It also shows here at the top the parameter values that are used. And then again, students you can just copy and paste these values if you want into something like Excel or another application. One of the other more complicated models is this case of still one-dimensional flow and one-dimensional dispersion. And here we have multiple solutes. So here are the governing equations. We're inputting in the input concentration, we have solute, we call solute 1. So we have the advection term and dispersion, we have retardation, and then this has first order decay constants, which are given by mu. And then this solute 1 decays to solute 2, and then solute 2 can decay to 3 and decay and up to 4 solutes we have here. In this case, the analytical solution is extremely messy. It's a Fortran code of about over 500 lines, but the students that we have working on this were able to convert all that into Java, and this is an example of the way we built the user interface. So we have the option of having a plot on the top and another plot on the bottom. And this is for you can see here, this is for 3 solutes, and these are the values of the velocity, dispersion, and this is the top plot is a fixed time plot. So this is the concentration versus distance of each one of the 3 contaminants. This is the first contaminant, which is decaying. The second contaminant here is in red, which is being produced from the decay of species 1, and then species 2 is decaying, and then species 3 is being formed from the decay of species 2, and then that's also decaying. Down here at the bottom, we decided that we could make a second plot, and here we decided to have it be a breakthrough curve, so concentration versus time at a fixed distance down here. And again, you can use these slider buttons and get the printouts of the concentrations, and you can get the raw by clicking the show data button. You can get all the raw data here. This is another case where this would be for multi-dimensional sorption, for three-dimensional sorption. So again, we have just one-dimensional flow, which is shown here in the schematic, and we have a continuous source of contaminant at a fixed concentration, and we have a rectangular source that we can adjust the size of this panel, and then this is just a continuous source over time, and here's the governing equation. You can see we have 3-dimensional dispersion, 1-dimensional flow, and we have the option of first order decay here. And this is what the solution looks like in this case. It's not very complicated. And again, we found this to be useful for more realistic 3-dimensional problems like leaking from maybe a landfill or an underground tank. And then the user interface looks like this. So we are just looking at a 2-dimensional cross section. So over here on the left are the input fields for all the values of the source and the velocities and retardation and dispersion parameters. And then this is where the 2-dimensional slice, we're looking at it at a different vertical slices. So you're able to slice this in different places in the vertical. And so here's what the slice looks like for this particular case. If you move the cursor over here, I could do a demonstration of this at the end. You'll get a printout of the spatial location and the concentration value. You can play around with changing the output, the way it looks, whether you have spoof shading or not. And then you have the option of doing cross-section plots. So here, if we've clicked the vertical cross-section, and then we are moving, we move the cursor here, and we're seeing this is a vertical cross-section at these 3 locations here. So the first location is closer in, so the concentration is higher. This is the second location, and then out here is a vertical cross-section at this point here. So these are just, again, just getting a plot across this one. The next one I want to show, and I'll do a demonstration of this since it's kind of cool, is this case of 2-dimensional steady flow. in a homogeneous aquifer with flow path tracking, flow path and particle tracking. So here we have a uniform regional flow. In this case, it's set up to be in a confined aquifer. And then we can have arbitrary extraction wells and injection wells. And we use potential flow theory to come up with the solution where we get the piezometric head, and we can compute analytically, we can compute the velocity here. And then we do numerical integration that is shown here along flow paths to track out the streamlines and particles. So at we start a particle, that we know from the analytical solution what the X and the Y velocity components are, and then we just track the particle. And then there's probably so many things you can change here, it's easy to get lost, but this is a screenshot of the output of what we call a doublet with regional flow and boundary particles. So here we have an injection, this is an injection well where my cursor is here. Over here is an extraction well, which is at the same strength, so the same pumping rate as this injection well. We can click a button here and we can change the color, shape, size of the particles that we're tracking from this injection well. And here we have uniform flow from left to right. And down here, there's this compass where we can adjust the direction of the uniform regional flow. And we can, down here, we can adjust the strength of the regional flow. And so you can see in this case here, all these red particles are injected from this injection well. They move here and they come around and they are captured by the extraction well. And then we're also releasing blue particles all along the left inlet boundary. So this would be tracking the regional flow. So you can see that you end up with like a groundwater recirculation zone here. And so again, sometimes this can be used for groundwater capture, trying to design well systems and pump and treat well systems and hydraulic barriers. Another, taking this same idea a little bit further, we built an applet that considers heterogeneous aquifers, again with flow path and particle tracking. And here I have to acknowledge work that was done by Dr. Paul Shea at the United States Geological Survey, who developed the original code in Java, and we made some enhancements to that code. So in this case here, we have a rectangular domain here, and we have uniform flow from left to right. And we have a constant head on the left, a lower constant head on the right, and impermeable boundaries on the bottom and top. And in this case, there's no analytical solution. So here is implemented a numerical solution by finite elements using linear triangles. So we compute the piezometric head, then we compute the velocities, and then there's numerical tracking of flow lines and particles. So here's a screenshot. I won't do a demonstration of this because it kind of takes a little time, but you can put in the number of elements you want along the columns and rows, and then what you can do is you can adjust the parameters, the hydraulic conductivity and the porosity. You can put in whatever values you have here. This is you have 5 different options, and then you can go in with your cursor and you can draw in different patterns of heterogeneity if you want. So I've done this where I've drawn in 3 patterns. The blue is a lower value, a higher value. This pink here is a lower value of hydraulic conductivity. The background white is this value. or you can click these other buttons down here and put in a random pattern of hydraulic convectivity. And then you can, click a button to track particle flow paths or do some particle tracking. And so this is for a particle flow path, and you can do forward and backward tracking. You can do animation, but what I've done on the next slide is I've clicked my cursor at these points here on the inlet, and then it tracks out these streamlines through here. Again, you can animate this if you want. You can put the cursor anywhere here in the middle, and it will track the streamline in the forward or the backward direction, whatever your options are. And then the other kind of cool thing you can do is you can again go with your cursor and trace out an inlet zone, and then you can have some particles released. So this could be, say, a zone of contaminated groundwater, and then you can click and you can animate this, and you also have the option of, so I'll show what happens here. Again, I just have some screenshots, so you can see that this high permeability zone where the particles went inside and then are being, the streamlines are moving outward, and then the particles are being diverted around the low permeability zone. And and so this we've used to illustrate concepts of macro dispersion and how heterogeneity can affect the spreading of contaminants. And one of the last ones I'll do here is talk about this newest one that we've developed, which is this interactive groundwater flow model to study groundwater stream flow interactions. And again, here we're going back to the other option, the other model, where we're running ModFlow basically as a web application. And maybe some of you are familiar with ModFlow, maybe not, but ModFlow is originally developed by the United States Geological Survey, and it's kind of like the by far the most commonly used software suite by government agencies, by consultants for groundwater flow. And so we have a ModFlow model that's hosted on a server here at the University of Illinois. The user sits there at that's the client, goes to their web browser and wants to make some modifications to the groundwater model. I'll show in the next slide what modifications can be made. So there's some scripts that are done here in HTML and other things, and this is sent to the server. Parameters are changed in the input files for ModFlow. The ModFlow model is run. All the output is generated and then sent back to the student here, the client, and then locally on the web browser, the student does some graphical output. And so here's the scenario that we set up. And the goal here is, this was developed as part of an education project. We actually worked with colleagues in the College of Education here on this project. So we wanted to enable middle school and high school students and undergrads to learn about aquifers and especially how groundwater pumping can affect stream flow. So we have this kind of schematic here. It's a two-dimensional ModFlow model in a big rectangular box. And we have kind of no flow along the boundaries. We have constant heads by certain, with a certain time history here at the top and the bottom. We have a river or a stream that runs straight down through the middle of this system. And this stream is fed by the groundwater here. And then we have a city over here that has pumping wells that the city uses for their water supply. We also have a farm set up over here that has some pumping wells for irrigation. So the farm pumping wells have seasonal variation. And so what the user can do is, and we also, excuse me, have a wetland here where the land surface elevation dips below the water table. And so what the user can do is the user can modify the pumping rates. The user can add additional pumping wells here for the city or the farm, and then look at what the impact of that pumping is on the stream flow. So there's a certain inflow hydrograph. So the stream flow comes in naturally, having some seasonal variation that's shown here. And then the output shows the seasonal variation, which you would get with no pumping, and then the impact of pumping here. And this is a screenshot here of what it looks like on the web browser. So you can see there's all these buttons up here where you can get some information. There's tutorial buttons. There's a button up here for a curriculum that our colleagues in the College of Education worked on, which actually, are for high school earth science curricula. And here is just a snapshot of, you can add, there's an animation of the water table elevation. You can see you have 3 wells over here for the city, 2 wells over here for the pumping, for the farm. This is the stream down here. This is a snapshot of the water table elevation. Blue is low, and let's see, excuse me. Yeah, blue is low and red is high. No, opposite. Sorry, blue is high and red is low. And then over here is a graph of the model runs for 5 years. And so over here is a graph that shows the stream flow, cubic meters per day over these 5 years. The top hydrograph, seasonal hydrograph, is the inflow. Excuse me, sorry, my mistake. The blue is the inflow here. That comes in the top. This gray would be the outflow, which would be what you would get if there's no pumping. So the groundwater would feed the stream, so we'd have a higher stream flow at the outlet than we have at the inlet. And then this dark curve here is the impact of the pumping wells. So, so again, all these options for doing the printing and the plotting are done locally on the browser. So I just have a couple more slides. What would we do if we're doing this in 2025 right now? Well, I would probably consult my colleagues in computer science and web development. You could write your models in JavaScript. So these will execute locally in a web browser. So this would be one option. And I'm not sure, JavaScript does have some math libraries, so you should be able to do scientific programming this way. Another interesting option, especially since Python is becoming more widely used, is to try to do everything using Python, where you can use something called Jupyter Notebooks as a user interface, and then Python would do all the scientific calculations. And then probably your typical undergrad does not want to learn Python, or may not want to install Python on their laptop. And there's something that I don't know too much about, but I know is quite popular here. It's something called Docker. And so you can have everything downloaded in a container. And that way, the user doesn't have to know anything about Python, doesn't have to install Python. They just need to install this thing called Docker. and then they download everything, and then it runs on their laptop, on their local computer, just like they had Python installed there. So these are some options if you're considering developing some new educational interactive software like this. So my last slide. I'd say that these applets have really greatly enhanced several courses here at the University of Illinois, Urbana-Champaign. We use them in the introductory groundwater hydrology class. They're used in advanced groundwater modeling, which is mainly just numerical methods, but the students use these applets to compare their numerical results with analytical solutions. They're used by my colleagues in environmental engineering, in contaminant fate and transport courses, remediation design, and also in a course that's called Physical Principles of Environmental Engineering. They're very handy to use in lecture demonstrations, and it's easy to incorporate these in homework assignments and projects. The reason that this was successful is I had a team of great colleagues and graduate students, and I had some civil engineering students who were savvy about computers, and that was a big help. But the other thing that was a real surprise, or kind of impressive to me, is that we worked with several computer science students that had absolutely no domain knowledge of engineering or partial differential equations or anything, but they were just able to help us and develop the interface and do the programming. And the last bullet here is I think, I really like it when I hear from colleagues that use these in their courses and tell me that they're useful. And I also like it when you tell me there's something broken so I can try to fix it. And I think in the end, I'm proud of all the research I've done and my scientific papers, but I am actually, I have to say, I'm most proud of developing and being kind of the main force behind developing these educational applets. So I'm going to go out of the presentation and maybe try to do some demonstrations, or maybe I could take some questions. Maybe I could take some questions first. I'm not sure what would be the best approach. So
I think I'm asking attendees to type their questions in the chat box so we can get to the questions at the end, but you could probably do the demo.
Okay.
That would be good.
Yeah, let me do that here. Okay. All right. So let me just share this other screen. It will. Let me see. Okay. Is that working? Do you see that screen?
Yes.
Yeah.
Okay. So this is the Edge browser. And again, I will go here, and so the two buttons, this is the button to run the applet from the web browser. So if you go over here, you'll see the instructions. You use this Java applet, you put in this extension. If that doesn't work, you download the jar file. But this is to launch the applet here in the web browser. This is the download button. So if I go here, and if it works, I'm hoping that we will see something. There we go. This thing. Okay. All right. Okay, so this is actually, I'm sorry, let me do this one here. I wanted to do the basic one-dimensional dispersion one. And again, sometimes this doesn't always work right. But here is a case. These are the different models. This would be for an instantaneous pulse. This is for continuous input. I can show this one here. But if you, these are all the parameters that you have here. You do compute. This would be, you see, this is a fixed position at time 10. Let me change it to a fixed time. That might be a little bit easier. Let me compute that again. And you can change the way you want the scale, the display to show, but then you here can do this cursor and you get the output. And if you want to look at, say, the impact of decreasing the dispersion coefficient, when you click multiple curves, we change the dispersion coefficient from 0.5 to 0.1, compute again, and you can see that there's less spread and the peak is higher. And you can look at the values, and then you can do the show data, and you get these results here for the data. So that's the way that applet works. I think that what I'm going to do now is show, figure how that one, there we go. What I wanted to do now is show this one over here. And this one, actually, I was playing around with this before. This one, there's some glitches when you try to run it through the web browser. So I did the download. So let me I'm going to share a different screen. So I'm going to. So in that case, I'm going to, well, let me do it this way. So if you go here, this would be the download. So I would click that. And there's the jar file, which is downloaded to my own laptop. I can open the file here. And now I'm going to share a different screen. Sorry. Wait a second, I'm sorry. That's the one I wanted to, okay. So here's this applet over here. So this is the one that had, and the one I showed before, the doublet with the particles. And so there's a injection well here, and you can click on that. Well, this is going to be a little bit cumbersome because these open up in different windows. So I won't do this, but you can, if you click on that, you can see what the pumping rate is and the color particles. And then if you do compute, you can see the pattern I mentioned before. If you want to change the direction of regional flow, you just move this little cursor here and compute again, and changes the direction of regional flow. If you want to grab the well and move it somewhere else, you compute again. And again, when you move the cursor, hopefully you can see that it's printing out the X and Y coordinates, and it's printing out the velocity values that are here as well. And then the other models, you know, you can insert a well, insert particles. You can do all sorts of things here that you can spend a lot of time with the tutorial. So I think maybe those are the only two I will show, and I'll just kind of take some questions. Now let me stop my sharing and just take some questions. Thank you very much.